there, and I'm back on the line again. And so when I draw this line, notice that we just end up with the same line again. Which kind of makes sense, like if you look at the equations, like if you look at the second equation, imagine adding x to both sides. You just get x plus y equals 5, right? So really they're the same exact equation, they're just configured a little bit differently, so they look different. So in this case, we have infinitely many solutions. Which occurs when they're the same line. Now we have to be slightly careful about infinitely many solutions. When we solved equations in one variable, and it had infinitely many solutions, we said that all real numbers were solutions, right? You guys remember that? We can't say the same thing here, because it is not true that every single point is a solution to this system, right? Like here's a point, that's an ordered pair, right? It's not a solution to the system because it's not on the line at all. So when we say there's infinitely many solutions, what we mean is that if an ordered pair is a solution to one of those equations, it is also a solution to the other one. We don't mean that everything is a solution to the whole thing. So we will say this system is consistent Remember, that means that it has at least one solution. So in this case, there's infinitely many. And it is dependent. Because I don't have two separate lines. So you can think of it as like whether or not an ordered pair is a solution to the first equation depends on if it's a solution to the second, right? Like any solution to one is a solution to the other, so they're dependent on one another. And then the last one, these are both in slope-intercept form, so let's just graph our y-intercept. Is at 0, -4. And then my slope is 2, so I'm going to go up 2 and to the right 1 for that first line. And then my second equation has a y-intercept at 0, 1. So like right there. And then it's also got a slope of 2. So I'm going to go up 2 and to the right 1 to get a second point. So here's my second line. And what do we notice? They're parallel lines, right? And in particular, because they're parallel lines, that means they never intersect. That's just the definition of parallel lines. So if they never intersect, that means there's no point that's on both of the lines. And so there is not an ordered pair, which is a solution to both equations. So in this case, we have no solution. So that occurs when we have parallel lines. And when that is the case, we say that the system is inconsistent. And really, that's enough to just say it's inconsistent, because it's impossible to be dependent and inconsistent. Like if you're inconsistent, there's no solution. If you're dependent, you're the same line. So you've got all those solutions. So once you say it's inconsistent, it's impossible for it to also be dependent. However, in my math lab, so like in practice, we just say inconsistent. In my math lab, they make you check both boxes. So it's also independent because they're two separate lines. So a big part of your online homework tonight is just looking at systems and classifying them using these words: consistent, dependent, independent, and inconsistent. So graphing is nice because it allows us to like see what's going on, but it's not super practical for actually solving systems, because as soon as it's not like a really nice like integer point, it's really hard to read exactly what that intersection point is. And so we have methods for solving these algebraically so that we don't have to always graph them and then try to like find that intersection point. So, oh wow, preview. So we are going to, there's two methods for solving systems, and when it comes down to it, both methods work for every system. Like you could like only use one and you could always do it. However, it is true that one is more efficient sometimes and the other is more efficient in other times. So I think it's convenient to know both and be comfortable with both. But if you find that you're just way more comfortable with one method, like I'm not gonna like tell you which one to use. Like you can do it however you want. So today we'll do substitution, tomorrow we'll do elimination. So we're gonna solve systems. Using substitution. So let's just do an example. Is probably the best way to see it. So we're going to solve x plus y equals 4, x equals y plus 1. So when I look at this, the first thing I notice is that that second equation like tells me what x is equal to. So it says that x and y plus 1 are equivalent, which means that I can use them interchangeably. Like anywhere I have an x, I could put a y plus 1 because they have the same value. That's what that equal sign means, right? And so if I look at the previous, or the first equation, and I come over here and I say, okay, well, I see an x, and my second equation tells me that that x is exactly the same as y plus 1. So I'm just replacing the x with y plus 1 because the second equation says I can, because x and y plus 1 are equivalent. Plus y equals 4. So everything else in that equation stays exactly the same. So the benefit of this is that I now have an equation that only has one variable in it, and we know how to solve equations that have one variable. And so we can combine like terms, and solve for y. And so now I'm halfway there. Remember, our solutions are ordered pairs. And so I have my y value. I just need my x value. Luckily, that purple equation tells me exactly how to get my x value from my y value. So I'm going to come back over here and say x is equal to, and put that 3/2 in for my y, plus 1. So x is equal to 5/2. Which gives me the solution 5 halves, 3 halves. So in order to use this process, we have to have one of the equations solved for one of the variables. So one of our equations has to have x or y alone on one side, and it doesn't matter which one. And if it doesn't come that way, we can manipulate one of our equations to get it. So does everybody have this one written down? So we see here that neither of our equations has x by itself or y by itself, but we can manipulate it. Like, we could choose either one. Like, we can solve either the first equation or the second equation for either x or y. It doesn't matter. It's totally your choice. However, there's usually a most efficient choice. So imagine if I was, don't write this down because we're not going to do this. Imagine if I was like, oh, I'm going to take that second equation and I'm going to get y by itself, right? So I would have to subtract 4x from both sides. And then like, oh shucks, I have to divide by 3. And now all of a sudden I have this expression with a bunch of fractions that I'm going to have to plug into another equation. And I mean, it just kind of gets messy, right? The reason I ended up with fractions is because I had to divide by that 3. So if you can identify a variable that doesn't have a number in front of it, doesn't have a coefficient of anything other than 1, then you'll never have to do that division, right? So in the first equation, we have that x plus 2y. And so I see that x, and I'm like, wow, it'd be really easy to get that by itself. I just have to subtract 2y from both sides. So x equals 6 minus 2y. So what I did the first time wasn't wrong, like it would work just fine. It's just a lot messier. And so I always look for those variables that have a coefficient of 1, just to make my life a little easier. And so once we've solved for x, we know that x and 6 minus 2y are equivalent, so I can come back to my second equation and say, okay, this is 4, and where I have an x, I'm going to replace it with 6 minus 2y. And then everything else in the equation stays exactly the same. Just replace that x. And now I see that I've got my single variable, which was what we were going for. So we'll distribute, combine like terms, and solve. So 8y plus 3y equals 4. Y equals 4. We're not quite there yet because we have to get x. So we're going to come back up to that purple equation. I mean, realistically, I can plug that y into either one of the original equations. But since this one tells me exactly how to get x from y, it's probably the easiest one to use. So we have x equals 6 minus 2 times 4. So just replacing that y with 4, and we end up with x equals -2. So my solution is -2, 4. Does this make sense? I think one of the keys to these is just organization. Like I have a way I do it, like I do 2 columns every time, like one for each equation. You can organize it however you want, but I would recommend that you come up with like a consistent way to organize it, because these problems, like you can end up with like things all over the place, and it's really easy to get lost in everything going on. The other thing that you want to make sure of is that you're always plugging, when you substitute, that you always go back into the other equation. So if I did this, and then I was like, oh, I'm going to put that x right, or I'm going to put 6 minus 2y in for x right there, I'm plugging that like back into itself. You will always get an identity because those two are the same equation. So you always have to go into the other equation in that step. The one that you didn't solve for, in this case, x. Okay, you guys ready to try one? I know you're really quite excited about it, I can tell. Okay, let's solve 2x plus y equals 6. Minus 3y. No, wait, oh, I'm sorry. Negative 10x minus 5y, that's what I wanted. Equals 4. About like, let's solve like 2y equals 3x plus 6, and then 6y minus 9x equals -18. I think that'll work. Oh, except I picked such a crap. That was stupid. Now we're going to have to do one with fractions. Sorry. So to solve that first equation for y, I'm just going to divide everything by 2. So we have y equals 3/2 x plus 3. And so then we'll plug that back into our second equation. So we have 6 times 3/2 x plus 3 minus 9x equals -18. Damn it. Close your eyes. Okay. That's a positive 18. It's been a positive 18 this whole time. Okay, so now we'll distribute. If multiplying by that fraction gives you anxiety, just get out your handy dandy calculator and just plug it in. This actually works out really nicely because 6 divided by 2 is 3. times 3, like just like when we're clearing fractions, gives us 9x. So 9x plus 18 minus 9x equals 18. So again, 9x minus 9x is just 0. So we end up with 18 equals 18. And so we have infinitely many solutions. Many solutions. Because 18 is always equal to 18. Good stuff. Okay, we have one more type of problem, which really isn't any different, it just looks different. So we are going to find the point where the graphs of f of x equals negative 3x plus 5 and g of x equals 4x minus 9 intersect. So even though it talks about graphs, that doesn't mean we have to graph it to solve this. Because just like we did at the beginning, the solution to a system is where the graphs intersect. And so we can solve the system algebraically, and we're finding that same point. So this looks a little bit more complicated because it's in function notation. But remember that when you graph a function, the output is just your y value. And so the graph of f of x equals negative 3x plus 5 is identical to the graph of y equals 3x plus 5. And the graph of g of x equals 4x minus 9 is identical to the graph of y equals 4x minus 9. And now we see that both of those are solved for y. And so we can just take this guy and put him in for y right here. So we end up with negative 3x plus 5 equals 4x minus 9. And it actually turns out that when your equations are in function notation like this, like you want your outputs to be equal, and so it always works to just set the functions equal to each other, right? So take the expressions on the right side of each and just set them equal to each other. And so then we can solve, let's see, 7x plus 5 equals negative 9. So negative 7x equals negative 14. And x equals 2. And then we'll take that and plug it back into either one of the functions to get our y value. So g of 2 equals 4 times 2 minus 9, which is just negative 1. So our point of intersection is 2, -1. So you guys see we're basically doing the same thing. Good. Cool. That's all for today.